Fortunately, C and C will get a reply for that request and help the node A to transmit packets to its destinations E. So so far so good. The node A can reach the node E, which it can never reach before. So what's the what's the drawback for this scheme? Actually, when the node A wants to communicate with node E, it is consuming the energy that's within energy of the intermediate nodes. That is to say, that in these intermediate nodes C and D is going to sacrifice their energy or resources to help other nodes. This sacrifice is okay when all the nodes belongs to one infrastructure. However, in wireless ad hoc network, not every node belongs to one infrastructure. So when this case happens, certain nodes will refuse to help relaying packets to the destiny. And such behavior is called selfishness in our species. So how to stimulate them? There are many strategies has been designed to stimulate this relaying cooperation. Basically, they can be categorized into reputation-based system and pricing-based system. In our cities, we are going to focus on the pricing-based system because it's more practical and easy to implement. The pricing-based system is trying to use incentives as the payment for relaying cooperation. So in the system, the intermediate nodes is trying to compete with each other by offering better prices for relaying packets, and the source nodes will compare these offers and select the good deal from these selections. So we know that successful pricing-based system need to satisfy must have these points, like the robust regulations for making transactions online. And this is because in wireless ad hoc network, the channel is not stable, and it is more likely that packets in transmission will be lost, and the transactions will be interrupted. So how to maintain these transactions and maybe make successful communication is very important. We also need the security strategies to ensure that certain sensitive personal information is protected. Those incentives that might have real value in the world will be protected and prevented from malicious activities. And the last and the most important thing is a reasonable pricing adjustment strategy must be involved in the system, because the most important thing is we need to maintain the fairness in the network. The fairness we will be explaining in next few slides. So these are the proposals for the strategies used in reputation-based system and pricing-based system. For example, the probability payment here for pricing-based system is proposed by Dr. Yang, which is mainly like a lottery game. So the payment is sending out along with the packets, and the intermediate nodes can get the payment as long as it received a winning ticket, which is also randomly sent out by the source nodes. There are many other strategies. We are not explaining that much here. So what are the issues with these pricing-based systems I mentioned above? Actually, when you look at them, all these pricing-based systems are assuming that the nodes has unlimited incentives in their account. So this actually prevents an edge node effect in the network. This edge node effect actually usually happen on the nodes that geographically at the edge of the network. So since these edge nodes has the nature that they has less connectivity at the edge, so they have less choice. They have less chance to participate in the cooperation. So that they also have less chance to gain money from the network. As you can see in this picture, the nodes in the center of the network controls most of the incentives in the network, and the nodes at the edge of the network will be unfunctional because they are lacking of incentives in the network. So we also here I'm going to introduce some terminologies that will be used in this thesis. First is the centrality. Centrality of the network is usually used to indicate how important that the node is in the network. So the more important the node in the network is, that the more probability that the node can take part in activities such as the learning cooperation. So here are four most famous centrality we use. That's degree centrality, betweenness centrality, closeness centrality, and eigenvector centrality. Due to the short of time, I will just introduce the first two. The one on the left is degree centrality. We use the blue icon to indicate a user or vertex in this network, and the number in the box beside the blue icon is the centrality of that particular vertex. So for the degree centrality, we define it as the connections that the user has in this network. So let's look at the user 2, which has two connections with the user 1 and the user 3. So the centrality of user 2 is 2 here. And it is obvious that the degree centrality is easy to calculate, but actually it only provides the local information of that user. So if you want more global view of that user in the network, you need to use betweenness centrality, which is indicated on the which is shown on the right side. The betweenness centrality actually is defined as the number of shortest paths of other nodes that goes through the selected user. As we can see, if we also look at the user 2 here, it has centrality 0 here, and that means it has there is no shortest path that goes of any other two users that go through the user 2. And more important is the higher betweenness centrality the user has, means the user is more important in the relationship of other two nodes. So if you change the position of that user or just remove it, it is possible. It is more likely that other nodes will have to change the shortest path that through the particular user. So our thesis is going to use a centrality called local centrality, which is derived from this betweenness centrality. We will talk about later.
Can you define what betweenness centrality is?
Betweenness centrality, as I mentioned before, is the number of shortest path that go through shortest path of other nodes that go through the selected user. Which here you can see if you say the shortest path from between 1 and 3, this one is the shortest path, right? And this one doesn't go through 2, so 2 user 2 doesn't have the shortest path goes through.
So for node 1, the betweenness centrality is 1 because the path from 1 to 3.
Because actually the shortest path between actually that is a ratio that the shortest path goes through the node 1 and 2 will be the shortest, and the number of shortest path that goes through 1 to the number of shortest path that within all the network.
So I think
how many shortest paths are in the network?
Like if we say that the shortest path is going through 2 nodes, right? Or let's say the shortest path between let's say the shortest path between 1 and 5, and it is the 1 hop, right? And there's only one shortest path that going through 1 and 5. So.
So 5 should be 1.
Isn't it the shortest part in 2 and 5 that is going through 1? In node 2 and node 5.
That's why it's 1, right?
The one centrality for 1 is 2 going that 2 is 1 to going to node 5, and that the shortest path is going through 1, so that
Got it.
I think what people want to understand is why is node 5, why is that a 0? Right? Why is node 1 a 1?
Well, because 1 sits on the shortest path between 2 and 5, but 5 does not sit on any shortest path for any other pair of nodes.
There's no shortest path that goes through 5, so that's why it is 0.
I think it's clear.
So it's not a ratio.
It's not right.
It's not a ratio.
It's not a ratio.
No, it's the number of shortest paths that go through this node.
It's not right.
Okay. So
this is the fairness of the network that we are going to talk about in later thesis. And the total capacity, there are 3 fairness that we are going to talk about. The first one is total capacity fairness, which we usually call the James fairness index. It can be calculated by this formulation, and the xi here is the xi here indicates the allocated throughput that allocated throughput for ith data rate for ith data flow, and the n here is the number of data flows in the network. this James fairness index achieves its best fairness, achieves its best when all the throughput is evenly distributed in all data flows in the network. Like you can see on the left one, if the total capacity of this system is 150 megabps here, if you evenly allocate the throughput for these three data flows, you will achieve the best fairness one. And also, if you allocate them throughput like this way, you will only get 0.7 for the fairness index. So actually, not every data flow requires the same throughput in the network. Usually, in most of the time, that user requires a small data rate in the network. To achieve a better or reasonable fairness in the network, we use maximum and minimum fairness. The basic idea is the system is going to meet the requirements of the nodes that are required, who require the least data rate in the system. So in this picture, you can see when there are three users who require data rate in the system, the one required 1 megabps and will be fulfilled for the first, then the 15 megabps, then the 100 megabps. In this way, the system will achieve the best fairness for maximum fairness. And for the proportional fairness, it is actually an alternative of max and minimum fairness, which is aimed to balance the efficiency and the fairness of the network. To achieve the fairness here, the proportional fairness is going to allocate and optimize the data rate, which is inversely proportional to the resources that have been allocated to that node, which is indicated by R here. So this one is a system view of log-element interactions. In short, is LGI. This LGI system is proposed by Professor Minsky. It is a mechanism that, for exchanging messages, which allows an open group of distributed agents to interact under the constraint of certain policies. So the best point of this mechanism is that LGI is trying to make strictly separation from between the policies and the policy independent executors, which is called controller here. So everything that the agents want to, everything that need to go into the network is going to be executed by the by this controller. This controller can be written in arbitrary programming language. The structure is not limited. So the only requirement for this structure is they use a message called message, which is.
So this is not relevant. Just go on.
So we are trying to use the LGI. We are trying to borrow some idea from the LGI, which is using some agents to solve the security issues in our system. This is the definition for some definitions in our system. Task is defined as transmission that involves a certain number of packets between two randomly selected nodes. The local centrality is the centrality that we use here in the system, which is actually the number of relating cooperation that the node has successfully participated in. With the definition of local centrality, we can define the centrality fairness as the variation of the local centrality within the network at time n. The local utility ratio is another local parameter for the node, which is the number of relating cooperation that the node I participate in to the number of the relating cooperation that node I has requested for. We also borrow the agent idea from the LGI, which in our system is wrap up for the LGI agent and the LGI controller that will take care of all the security issues. The wallet here is a container for the incentives of particular user. It also take logs for the transactions that going on with that user. We use digital coins in our system to as the incentives for relating cooperation, and the balance is defined as the amount of digital coins held by the user. And we also have some assumptions for our system. For each user, there's only one wallet and one agent is assigned to that particular user. Now obviously we can have two, but several, but one is enough here. And every wallet will have a certain amount of deposit initially, and the maximum balance for the wallet is unlimited. So every wallet can have as many incentives in the wallet. So, and also the only way for the user to earn incentives in the system is to relay packets for others. And the system, the total incentives in the system is fixed. We also use the digital coins as the real coins, which means you cannot split the digital coins into halves, and the minimum denomination of digital coins is 1. All nodes are supposed to be well behaved and trustworthy. The link status is also assumed to be stable, which is not very true. And the payment is based on every packet being transmitted.
But it's not really true. Why do you make that assumption?
Sorry, that it's just assumption here, but it's not, we both know that it's not true in the real world. So every emulation
You're saying your whole work has no meaning.
Not really. We are trying to simple the experiment as possible, but still we keep some character of the real thing.
So, just quick feedback there. You shouldn't have said the second half of your sentence. You opened yourself up for that right there. All right.
And we also randomly choose every task and randomly choose every node involved in each task. We have designed the strategy of pricing adjustment. all of them have all of them are following the same main idea of pricing control, which is trying to control the unit price of semi packet.
So I'm not sure I understand your problem definition.
Sorry.
So you're starting to describe mechanisms. What do you actually want to do? What's your goal?
My goal is trying to improve the fairness of the network and by using the strategy of pricing adjustments.
So you're trying to maximize the James Fairness Index?
Not James Fairness, that's the local centrality, which I define for the fairness.
Okay.
So,
have you actually explained what local centrality and fairness is?
yeah, in previous slides.
Yeah, I know you had the equation there, but can you tell me what S is?
This one is local centrality.
So what is S?
S actually is an indicator function here. It has the value 1 when a node is successful in participating in the relating coefficient. So when you add them up, that is the total number of the relating coefficient that the node has to take from it.
And you just sum that over all nodes?
Yeah. Oh no. This one is for a particular node K.
We calculate the variance.
That's a local local.
You calculate the total number of packets relayed for each node.
Yeah, the fairness here we are trying to.
Variance overall.
Yeah, I calculate variance for all the nodes.
And what's the connection to all of these other fairness schemes that you went through?
This local centrality is actually from the previous centrality, but I didn't say this fairness has connection to this fairness connection.
Oh, so we don't actually need to understand the others. This is what
No,
you make.
that's just
For education.
so. This is all three strategies of pricing adjustment is sharing the same main idea of controlling the price for relating cooperation, which is you trying to control the unit price.
I still need to question you a little bit on that. So now we're trying to optimize this notion of fairness. We're trying to equalize the number of packets forwarded by each node. That's the goal, right?
Equalize the
number of packets relayed by each node.
Not really. I think we are trying to equalize the chances that node can take part in, can participate in relating cooperation, so that every node can get equal chance to gain incentives from the network.
Is that the same as the fairness metrics that you were describing? You were describing this fairness metric, the variance among the number of packets relayed. And you're trying to minimize or maximize the variance?
I'm trying to minimize the difference because I'm trying to eliminate the differences between different nodes.
So that means you're trying to aim for every node forwarding a similar number of packets.
What he's saying is, yes, basically. He's saying though randomly different connections might exist. He's not trying to predefine that this node will have exactly the same as that node. He's trying to say that they have the same. They have a chance to have the same. But if all communications happen to be on that half of the network, then there's nothing you can do about that. So before you go on, actually, I think we need to go back to your original. Don't go back. Just the cartoon. Don't. The cartoon that you had earlier with all the nodes in the middle having all the money and all the nodes at the end having no money at the edges. Really what you're trying to do is make certain that all the money doesn't end up in the middle of the network. And so what you're not saying here is that really your notion of fairness, which is related to people getting an equal chance to relay, all right, is really about preventing all the money ending up in the middle of the network. All right, so maybe that's another way of looking at it, which is if by having fairness, we kind of extend the lifetime of the network, which means the money stays out at the edges longer than if you don't do your pricing.
So actually you can.
So do you have a complete problem definition? So it sounds like you're trying to minimize fairness, but not at all costs. There's some other constraints that you have.
To minimize the
so not minimize fairness. I mean, minimize the variance.
Yeah, minimize the variance.
So this notion of fairness turned out to be sort of a proxy for trying to keep the lifetime of the network in terms of money in the wallet for every node. Right? It's sort of a proxy for trying to keep it as, I don't know what to call that, as long as the duration until when you run out of money.
I have a question. Yes. How is money related to resources, like power and matter? Is there any?
Well, that would be Orion's work or something, right? That's not here nor there for this. All right. It could also be related to your PayPal account.
Yeah. So the price for the packaging, the pricing rate here is the unit price for sending a byte in the network. So you can simply calculate the price for one packet by multiply the pricing rate with the number of packets, number of bytes that packet has. So actually, when for every node, it will log the parameters that it want to monitor periodically, and this and the pricing adjustments is also going to be taken periodically in the period of time. This period, this pricing adjustment period is much larger than the logging period, so you can take the logging values as the real-time value for when you do the pricing adjustment. So for each pricing adjustment here, the node is simply compare the control variable, simply compare the differences between of the control variable and decide whether to adjust the price for the next cooperation or not. This is a detailed structure of a node that I mentioned before. So every user is attached to an agent and one wallet, and the agent is a wrap-up for the LGI agent and the LGI. And all the security issues and the communication issues will be taken care of by the agents. So this is a table for the pricing adjustment strategies I mentioned. We call it mode 1, mode 2, and mode 3, which is using different control variables, balance, local centrality, and local utility ratio, respectively. The detail of calculation is given on the right. As you can see, they sharing the same main idea of controlling the pricing. So, for example, in mode 1 is, for example, in mode 1, it is using the previous balance and current balance to control, to decide whether to add or deduct the step size from previous price.
So go back. Since these equations, go back one slide. Since these equations all look the same, you can take a moment. Let's take mode 1. All right. At time n, you're going to update the charging rate from time n minus 1 according to 1.
So for the time n, this strategy is trying to calculate the price for the next relating cooperation by add or deduct the step size from previous price for the relating cooperation. This action actually is dominated by the difference between the current balance and the previous balance. Also, we introduce some threshold for that difference to control the right time for the pricing adjustment.
So if my balance now is less than my balance previously, all right, then what's going to happen?
If the balance is less than previous one, that means I spend out the money without gain. So I'm trying to decrease my price for the strategy in this strategy to attract more cooperation to those. So before we go into the experimental results, I'm going to show you the setups for the common setups for the experiments. We use the object testbed to do the experiments. We didn't use the 400 nodes in the testbed. Only choose the 8 nodes to build our topology. For every experiment,
You've got 10 nodes. Yeah, we can all read.
Okay. So for every experiment, we include 600 tasks, and all the tasks involve the relating cooperation. The amount of digital coins, initial digital coins in the wallet is 3 million coins, and the initial pricing rate is 1 coin per bird. The time for the transmission node is 2 seconds. If we could calculate the connection and disconnection time, it's 7.5 seconds in total. And the length of per packet is 500 bytes. For the task velocity is 10 samples per second. We start from the static topology, which is S1 and S2 here. The one on the left simply has 2 additional paths that between 2 and 4 and 2 and 5. However, these additional 2 paths change a lot. Lots of for that topology. So first, let's look at the comparison of balance of node 1 for strategy S1 and S2. The red line indicates the results from topology S1. Apparently, the behavior of node 1 changed a lot when the topology changed. In topology S1, node 1 cannot get any incentives from the network. The balance of the node 1 is dropped down directly to 0 when the time comes to around 500 seconds. However, in topology S2, it still can get some incentives from the network, so it has incremented the balance, and also get a longer lifetime in the network. This huge difference is actually because these 2 shortcuts between 2 and 4 and 2 and 5. And the reason behind that is the node at the corner, which is node 1 and node 3 actually cannot provide a price less than 0. Even if these nodes want to provide help without any rewards, they still cannot get the chance to participate in relating cooperation.
So what if the traffic is very high? In that case, actually, going always to the shortest path is not the best idea.
Even if the high capacity here, you still
one
need to
is
go
not
through
related
these two.
because one is not on any shortest path.
Yeah.
But what if the traffic is so high that the shortest path is saturated? You have to go to a.
So he's not considering any of those issues. He's saying that by that point, node 1
But
is useless.
actually, I don't think that matters because even though those traffics all need to go through node 2 and node 4.
Well, what she's saying though is that you could have
Yeah, I
further
know.
policies that say
Like
Then
load balancing of it.
They go to non.
split
They go ahead and choose more expensive nodes.
into paths.
So, yeah. There's no link capacity.
No.
And those lines between nodes are wireless links.
Yeah, wireless links. So this is another comparison of the previous experiments in centrality fairness that we defined in the system. As we can tell, the smaller the centrality fairness is, the more fairness that the network has. So in this one, as you can see, the topology S1 has increased its centrality fairness very fast. That's because those two nodes at the corner is always have the local centrality. So the difference between these two nodes and other nodes have become larger and larger than the other nodes. So we also studied the balance of the node of A node.
So did you actually run that experiment longer?
No, I didn't
What
extend
happens?
No,
Is there a steady state that you should look at?
actually, I don't think it will get a steady state for this one. It will keep increasing if you keep the experiment running.
Is it infinite fairness?
You know, it's kind of this fairness definition.
I didn't normalize it.
It's just, if first second I send 10 packets, next second I send 10 packets, then it's 20, then it's 30, then it's 40. Right? And so there's no normalization by saying how many packets per second in this definition. So
You're
the
looking at the
variance
variance.
by the difference. Yeah, so the variance is
Variance.
it's two nodes have 0 always, and then the other nodes have 10, then the next second they'll have 20, and then the next second they'll have 40, because he's not saying amount of packets per second, amount of packets per unit time.
So what you're plotting there on your y-axis, what is that?
That's the centrality fairness.
That's the variance.
That's the variation.
It's basically centrality unfairness. Higher numbers means more fair.
Yeah. So we also studied the balance of the nodes in the network. All the balance of the 8 nodes into topologies follow the same patterns. If you can tell that the more centrality that the node has, the more balance that the node can accumulate at the end of the experiment. I think this is because the local centrality is defined as the number of cooperation that it takes part in the experiments, so that it can much more in the network. We also, to eliminate the effect of the edge nodes, we designed we provide the mobility to node 1. So node 1 can go through the network and change to new positions in the network. First initially is left upper left corner of that topology, and then it goes into the network. Finally, they end up at the new position of the upper right corner of the network, which is also an isolated position. So with the mobility, the node 1 changed its behavior, obviously. When the node changes its position here, the balance of the node 1 start to increase, and this increment continues when the chain finally got to the position that still got isolation. So it start to decrease, just like before.
So go back. At the very end, the guy's balance is flat.
This is not in the experiment. It's stopped the experiment.
Oh, sorry.
Yeah. So do you want in the dynamic topology, we also studied the centrality fairness of these two topologies. Apparently, the centrality fairness is much better in the dynamic topology. We have around 40% improvement in this. We also studied the balance distribution in the static topology and dynamic topology. As you can see in the static topology, in node 1 and node 3 actually has no share of the total incentives in the system. The node 2 actually have controlled the 44% of the incentives in the network. When we have the mobility here, the dynamic topology D1 has the node 1 22% of the incentives in the network, and the node 2, the incentives in node 2 decreased to 25%. Almost half of the nodes has the same share of the incentives in the network, which is around 20%. So for the first part of the experiment, we summarized that shortcuts may prevent the nodes from the cooperation. The balance here has relationship to the local centrality, and mobility can include the fairness of the networks. For part 2, before we start part 2, we are trying to prove that our pricing adjustment strategy works. So we put them to static topology. And this result is from 2 different topology. This one is for the S1, this one is for S2. As you can see, the strategy works fine in S2, but in S1, actually it doesn't improve much. This is because the S1 still have the shortcuts in the topology, and it cannot be eliminated by the strategy. Still, the nodes cannot provide the prices less than 0.
Do you think it improves fairness when you were showing me plots of balance?
No, this is trying. Next one is the fairness. This one is trying to show the behavior of the nodes didn't change a lot. This one is showing you the fairness doesn't improve also. So, and in topology S2, you can see the fairness get the improvement. So that means we have to change our topology to the new topology, which has no shortcuts in the topology. So we use this new topology. And to mention that we didn't use the dynamic topology because we want to study our strategies. We don't want to involve any effects from the mobility. So the new setups for experiments is introduced by the strategies. So first one is pricing refresh rate, which controls the minimum time between two pricing adjustments. And pricing adjustment step size is set to +1. The thresholds for adjusting prices is set to 0 for mode 1, 1 for mode 2, and 1 for mode 3. Here we actually can set up the different separately set up the threshold for increase and decrease in the step size, but we use the same thing. So the first one is we try all three strategies in the new topology, and we got that all three strategies work fine. And the fairness here is better than no adjustment here, which is indicated by the light blue line in this graph. We also studied the lifetime for that network.
So why is it that mode in the previous slide? Why is it that mode 2 is the worst of the three?
Actually, I cannot explain this.
Okay.
That's why I will do the experiment 3. So this lifetime is actually the number of packets sent out in this network in total for the time for the entire experiment. So when the topology is with no adjustment, as you can see, the increment is end up here around 1,500 seconds. So after that, there's no more increment in the packets sent out in the system. The network is kind of infunctional. So for other three that with the strategy of prices adjustments, they all have the increment in the packets that sent out in the system. Still, we cannot tell which strategy is best with this figure. So this is a stage summary for this part. We designed all three designed the pricing adjustment strategies works fine, and they can improve the fairness. However, we can hardly tell which one is the best. So we decide to adjust the parameters in the strategies. First, we tune the minimum time between the switching.
You really need to wrap up.
Yes. So first, we fine-tune the minimum time between two adjustment time, and after that, we fix the adjustment and fix the time between adjustment and fine-tune the step size. So in this page, I show you the results from changing the minimum time pricing adjustment rate. Where all three strategies surprisingly didn't give us the same didn't give us the right time on the best results. So for mode 1 and mode 2, it achieves their best when the tau is set up to 30 seconds. And mode 3 achieves its best when tau is set up to 60 seconds. We also observed that the mode 2 actually is more sensitive in setting these parameters, because every time you change the tau, you get totally different values. And also to so after that we fix the adjustment rate and we change the step size for further research. And this time all three strategies have their best when we set up the step size to point 1. So we compare the fine-tune the results for three strategies, and we find the best one is the mode 3, which has the when it has the time set up to 60 seconds and the step size set to 0.1. So after all these experiments, we conclude that topology is the most important thing to the network. So we cannot eliminate the effect of the shortcut in the network. But still, the strategies can improve the fairness of the network. However, the mobility can change the fairness, and that means if you move to the center of the network, you get more fairness for that network. And if you find a new position that with isolation, so the fairness of the network will be